Hi everyone, this is CHEN 121, week number 10, March 29th, 2021. And this week, I guess it's not plotting, it's linear regression in Python 3, right? So what we're doing this week is, again, we're trying to recap a bunch of different ideas we talked about in the previous week, specifically, um, creating linear fits, creating straight lines to fit experimental data and determining the R squared values, etc. However, this week we're dealing with a different set of data, so just practice on a different set of data and really try to hone in on these skills, or try to practice them a bit more. Okay, so we have this data measured in lab. We have two salts, NaCl, KCl. We ran a bunch of experiments at a bunch of different temperatures. For NaCl, 800 to 916. For KCl, it was from 776 to 905. And you measured a bunch of parameters. You measured the refractive index. You measured the frequency and the velocity at 90 degrees. You measured the frequency and the velocity at 139.9 degrees. Okay, so you have a, 1, 2, 3, 4, 5, 6. You have 6 series, 1 independent, 5 dependent for 2 salts. Okay, so what do we want to do this week? Let's have a look here. Using Python, write a script to generate the following plots. For NaCl at 90.1 degrees, generate a 3x1 figure for temperature versus refractive index, temperature versus frequency, and temperature versus velocity. Okay, so we'll generate just 3x1 figure. Each figure should compare the experimental data to a linear fit equation estimate. Okay, so we want to create three plots next to each other containing the experimental data for refractive index, frequency, and velocity at 90 degrees. So I'm specifically looking at these 4 rows here. And for each one of these 3 lines, I'm going to have the experimental data points plotted, and then I'm also adding a linear fit or a straight line estimate to compare it to the experimental data points. Okay. And number 2, we want to create a table summarizing the results for the slopes, intercepts, and R squared values. All right, so this is a bit new, creating a table for the different results. We'll talk about this in a second. Creating a 3x1 figure, we've done this before. We're just combining, I guess, different approaches, a subplot with, determining a linear fit and determining an R squared value. Okay, so let's go. And this set of data was previously used in week 7, number 7. So I'm just adding a comment here, so you can just load up your week number 7 script and modify it, or copy some aspects of it into a new script. Okay, let me go to Spider, and in Spider here I already have. So this is what we ran in week number 7. Or this is the script we had in week number 7. Let me run it so that I remember what we did back then. Oh, okay. So we generated plots next to each other, on top of each other, and we just draw a line through these plots. This is not a linear fit. This is just a line connecting the dots, right? It's a different thing. So what I'm going to do is I'm going to create a new script. I'm going to, let's see, copy these guys at the top here, right? Just the experimental data we have. And I'm going to paste it here. So I'm just copying, importing the libraries and importing just the data that I input. I'm just importing all of them. You can import, you're going to need to import all of them because you need to practice the rest of them as homework. So it might be a good idea. Anyways, so we imported our 3. Let me zoom in a bit. We imported our 3 typical libraries: NumPy as MP, Pandas as PD, matplotlib.pyplot as PLT. And then we're going to import the two other libraries we use for curve fitting and linear regression. So if you recall, we said from scipy.optimize import curve_fit, and then again from scipy.stats import linregress. Okay, so I just imported the curve fit function and the linear regression function as well. All right. So what do we want to do? Let's just try to remember what we want to do. We want to create a 3x1 figure, and on every figure, I want to have the experimental data and my linear fit for NaCl at 90 degrees. So I'm really concerned about these four, interested, I guess, about these four lists. And if you recall from last week, we created a robust code, to just do so, to just generate a plot and calculate the R-squared value. If you recall from last week, I should have it open here. We created this robust code where basically you just change the X and Y to 1 over CA. We were dealing with CA, so in this case, you can just change this to T NaCl and or NaCl, whatever, and it will give me my linear fit, and it will give me my R-squared value. So let me copy this structure, and you can see here now it makes sense, right? Because creating a robust code makes it easier to implement these changes much quicker. Okay, so I'm just copying this block of code which we have, which will do this for you, and I'm going to run a test run. Let's call this temperature versus refractive index for NaCl. Just to test, see if it's going to work. And if we recall, the only changes we had to make was for X. So now I'm going to give the X the value of this list, T NaCl, and my Y, I want to try the refractive index. So I'm going to call my Y R_NaCl. All right. And this should be enough. Let me change this. The correlation now will be R is equal to T plus B, right? And if I plot my figures here, I'm going to have not time now. This is temperature in Celsius. This is refractive index, and this is basically temperature versus refractive index, right? So let's run this as a test and see if it's going to work. What will it give us? So if I run it, you can see it worked fine. It's telling me the correlation is R is equal to slope multiplied by T plus B. R-squared value is this, and I generate a plot, refractive index versus temperature. I have my data points and I have my straight line. Okay, so let's do this for the rest of the lists we're interested in, and then we're going to deal with the subplot issue. So first of all, I'm going to generate the 3 plots, and then I'm going to modify my code to make it to subplots, right? So let me copy this first. I'm going to copy this block as is, and I'm going to go here. And now instead of refractive index, what did we want to plot? We wanted to plot F, which is, let me go back, frequency and velocity. Frequency is in gigahertz, velocity is in meter per second. So if I go to my second block here, so now it will be temperature versus frequency for NaCl. And this is a comment, I'm just putting it for myself. And now my y-axis, instead of R, I'm just using F90 NaCl, right? Print the correlation now will be F, and I'm just changing the Y labels. So the Y label now will not be refractive so that my plot shows properly. It will be frequency in gigahertz, right? And my plot title will be temperature versus frequency. Okay, let's run this guy and see what we're gonna get. So as you can see, we're getting a second line correlation is R equals this. R squared value, and then the correlation is F equals this and the R squared value. We're getting the two plots as the same color because we just copied the script. Let's change the colors. Let's make it look good. So I'm gonna change my refractive index to red, right? And I'm gonna change this guy to blue. I'm gonna use red, blue, black. I think it's a nice color combo. Okay, here we go. First one is red, refractive index. Second one is blue. Temperature. Let me copy it a third time and do it for velocity now. All right, so I'm copying it a third time here, and I'm just doing it for velocity. So now it will be temperature versus velocity for NaCl. And the Y here, I just changed to V. And this, you can see that this code is very robust. And over the next weeks, instead of copying it and pasting it every time, I'll just create a function which does this for me automatically, right? So I can just call a function. We can call it, one-to-one fit function, whatever. And we just put in the Y in the function heading, and it will do all of this for us automatically, right? And when writing Python, especially for things which are repetitive, so let's say you're doing a calculation when you take your numerical methods course, whatever, have to repeat it 10, 20, 30 times. Try to create a robust code, which is easy to change. So it's easy for you to repeat these calculations quickly, right? I'm just changing my output, printing the results as it tells me correlation is V is equal to this. And then I'll change the labels on my plot. Y label will be velocity in meter per second, and the title now will be temperature versus velocity. And I have my 3 lines to generate and print my R squared value using the linear regress function. If you forgot what this linear regress function is, please go to last week and revise it, have a look, make sure you're on the same page. If you're not, come and see me. We'll go through it, and we'll take our time absorbing this information. Okay, anyways, let me change the color here to black. And here it will be KO, because again, when trying to use one letter to represent black, it's usually K in Python to do so. And if I run it, I should get 3 plots, right? 3 plots, one for temperature versus refractive index, one for temperature versus frequency, one for temperature versus velocity. And I should get basically 6 lines of output. 3 lines are correlation of is R equals basically refractive index as a function of temperature, and the R squared value for this. Second one is F equals and the R squared value for this fit, and third one is V equals and the R squared value for this fit. So I'm able to get the straight lines, I'm able to get the R squared values, I'm able to generate 3 plots. So now let's modify this code to create the blocks in a side by side in a 3x1 figure. Okay, so if you recall, when we were doing this, to create a 3x1 figure, we need to first of all create a figure handle. And we talked about this weeks ago. So to create a figure handle, I'm going to use fig, which is the command axs1. I'm going to call this figure axs1. You can call it anything you want. plt.subplot. And now I want to create a 3x1 figure. So I want to create 1 row and 3 columns, right? Row, columns, this is how it goes. Row, columns, I want to create them as sort of long vertical figures side by side. I don't want to create them as horizontal figures on top of each other, because horizontal figures tend to be squeezed and they don't look too nice. I like creating the columns next to each other, right? So this will be 1 row, 3 columns next to each other. Okay, so now I have my handles, AXS, I have 1, 3, and now I need to modify the code to fit this. So let's go down here and let's look at the plot commands for each one. Okay, I'm going to remove this plt.figure because I don't want it to create a new figure every time. I just wanted to plot them all in the same figure. And then here, instead of having plt.plot, if you recall, I will use the handle axs0.plot. Instead of having plt.plot, I'll use axs0.plot. Sorry, we called it axs1. So I'll just use axs1. axs1, make sure you're not missing on these names. axs1, 0. axs1, 0. And axs1, sorry, 1, 0, right? So this should be sufficient to create the first part of my subplot, right? All I did is I changed the PLT to axs1. So PLT holds, or PLT is the handle for the plot. axs1 now is the handle for the subplot, okay? So I'm just changing the handle, telling it, don't drop these lines on a separate plot. Please drop them on the subplot in location 0. And as you can see here, I only have one number because it's only one row and 3 columns. So my indices will be 0, 1, 2, right? And Python can figure out, 0, 1, 2 from left to right. You don't have to put, 0, 0, 0, 1, 0, 2. You don't have to put 2 of them. It's redundant. If you have 3 by 1 by 3 or 3 by 1, if you only have one row or one column, you just use one index and Python will figure out what you're talking about. If you have 2 by 2, here when it starts that you need to use, 0, 0, 0, 1, 1, 0, 1, 1. If you have 2 by 3, maybe you have to use these two sets of coordinates together to identify which plot you're talking about, okay? But if you have one row or one column, only one number is used as an index and Python figures it out. That 1 row and 3 columns, 0, 1, 2 from left to right. This is the handle for the left figure, this is the handle for the middle one, this is the handle for the right one. So let's test run this, and hopefully you should get a 3 by 1 or 1 by 3 figure with only the left plot filled in. So let's give it a try. Hopefully you don't have any sort of strange errors. It seems that we do. So it's not happy about something. Let's see. What is it not happy about? Fig axs plt dot subplot. Oh, okay. We have a spelling error here. It should be plt dot subplots. Right, just be careful, with the syntax again. Issue is all of this error doesn't tell me anything about this error, right? So you just have to be careful, right? Let's try it again. Again, it's not happy. Axis subplots has no attribute X label. Okay, so it's not happy about this. So if you recall, when doing subplots, we don't really use X label and Y label separately. So the right syntax to use with subplots, AX is 0, and we did this before. We're going to use set, and we're going to say X label equals, and then I'm just going to copy this guy here, right? Y label equals this guy, right? So when doing subplots, you want to put the X label and the Y label on the same line using the set function, right? So these two lines are incorrect, and this is what this error is about. So let's delete them. Let's troubleshoot it. And again, when putting the X label and Y label for subplots, you put them under the set command, right? So axs.set, open a bracket, X label equals this, Y label equals this on the same line in the same brackets. Let's run it and see if we get any errors. Again, it's not happy. Why is it not happy? axs.title, set temperature text, object not callable. Okay, so it's not happy about this title. And again, I think with subplots, instead of using title, similar to a plot, we need to use set underscore title. I think this is the correct function for this. Now let's run it and see if it works. Here we go. So now it works fine. I get this, so I get the two subplots legacy from the previous code. 1 second, it's frozen. And I get my 3x1 figure, you know, first one is filled in, and then we still have issues, you know, we're running over each other. We're going to fix this at the end by putting the tight layout command, if you recall. I don't like this title. You see it's starting to run over the next guy. So I'm going to remove this title line. So I'm just going to comment it. I don't want it to have a title. Otherwise, we'll just have 3 sentences all over each other. Let's avoid this for now. Okay, good. So I did it for the first one, which is temperature over CA. Let's modify the other codes for the same thing. Let's just modify them. It doesn't matter. We don't need to really retype it. You can just type it again. You can copy and paste and make the changes. I'm not going to do that. So again, I just go to my, so first thing I'm going to do is I'm going to remove the plt.figure because I don't want it to create a new figure. And then here, instead of plt, I'm going to put the handle for the subplot, which is axs1. Again, for plt, sorry, we called it axs1. axs1, 1. And then instead of the X label and the Y label, I'm going to say axs1, 1. And we're going to use the set command. Set X label to be equal to this guy right here. Oops. And Y label to be equal to this guy right here. And I'm going to delete these 2 guys. I'm not going to add a title, so I'm going to delete this line as well. We said we don't want to add a title because they start going all over each other. It doesn't look good, right? Let's run this guy now, and hopefully we'll get the second plot show up. If there are any errors, we'll troubleshoot them. It's fine. It's not a big deal. Okay. So when you run it, you can see I get my first line, my second line. Again, we have this issue. They're all over each other. We're going to use the tight layout command to fix this. But for now, let's just move on to the third plot we have, which is this guy. And again, same thing. I'm going to delete plt.figure because I don't want it to create a new figure. I just want to put it on the same line or on the same figure. And instead of plt, I'm going to use axs1, which is the handle 2 in this case, right? Instead of this guy, I'm going to put axs1, 2. Instead of this axs1, 2. And again, for the X label and Y label, I'm going to use the set, dot set, and X label now is equal to this, comma, Y label is equal to this, right? So I set my X label and the Y label. I'm deleting this guy because I don't want the title. And this is all really for the third subplot. Let's run it. You should see the third subplot as well. Since I have my 3 lines next to each other, you have some cosmetic issues with that they're going all over each other. So let's try to fix this. So to fix this, I'm going to add the line fig dot tight layout, right? I really like this command. Please don't forget it. It cleans up your side-by-side figures or your, subplots very nicely. So once I add this line fig on dot tight layout right here, you can see it cleans it up very nicely. And now I have my 3 figures next to each other. Not running all over each other. So this is what we did. Let me recap. I took our code, which we did from last week, to get the slope and to get the R², and I just modified it so that it plots the lists we're interested in. And then I generated the subplots. Again, figure axis plt.subplot 1, 3 to generate 3 columns, one row subplot, and I modified the figure, or I entered the commands for the subplot. AXS1 is the handle for the subplot, basically defined here. AXS1, you can call it whatever you want. You want to call it, I don't know, SP1, whatever, just do. You can call it whatever you want, really. Just understand that this is a handle, it's not a function. It's not an important syntax thing in the library you're calling, it's just a name. And then 0 is the location of this. Plot the red one on the left. I'm plotting my line. And then AXS 0 on the same plot, I'm plotting my experimental data. AXS 0, I'm setting my X label, my Y label as well. And then I have my little code to calculate the R² value and print it out. Do the same for the other two plots. And again, once you have it for one and your code is robust and working, you can copy paste it. Just make sure to change at the relevant points. So in our code, or the code we're going with in this course, if you're doing the same, if you have something else which is working for you and you're happy with it, go with it. I don't mind. But if you're following what I'm doing exactly, for this code to be robust, I need to make sure that the X and Y refer to the lists which I am interested in, right? So in this case, X is the NaCl, Y is F90 NaCl, and everything else just runs normally. You just have to do some cosmetics, in terms of the output, in terms of, labeling your X and Y axes, just so that it looks good and makes sense. Okay, and this is what we have. So we're able to generate this one. Let's go to our lab here. Yeah, let's have a look. What else do we want to do? So this one is done. Second one, we need to generate a table summarizing the results of the slopes, intercepts, and R² values. Okay, let's try to generate a table. Let's have a look. So our output at the moment is just a bunch of lines here, correlation is this, R² is this, and as an output, it's not the best thing visually, right? So we want to generate a table to do so. And now we're using the pandas here, right? So we haven't used pandas before so far, but now we will be using the pandas library, and the pandas library is really the one which will help you generate tables, or it's the one which is used to generate tables. Sometimes they're called data frames, to present your data in a nice, easy, presentable way. Okay, and to generate a list of tables, we need to generate lists, right? So let's generate a bunch of lists, right? Because before putting them in a table, so here I have 3 slopes, 3 intercepts, and 3 R² values, right? I need to put them all on a list, and then I can, copy these lists into a table, right? This is how the logic is going to work. Otherwise, you're going to have to rewrite the code for the table every time and just append it to the table, which might make your code clunky, right? You don't want that. You just want to create the lists, and then at the very bottom we'll deal with this table issue. So for these lists, I'm going to create 3 lists. I'm going to call them slopes. And at the moment, they're just empty lists. Second one will be intercepts. Again, empty. Third one is our values. And again, it's an empty list. You can call them whatever you want. But these are the list names I'm going to do. And what I want to do is, within every block of code dealing with one of these plots, I want to append the value for the slope, the value for the intercept, and the value for R² into these lists. Okay. So at the bottom here of every one of them, I want to add 3 lines. First line will be slopes.append A, and A is the slope of this line, AX plus B, right? So I'm just adding this A to this list, and then I'm going to have intercepts.append, what's the letter we used? AX plus B, so append B, right? And finally, or values.append R², which is right here, right? I just want to append this value to this list. So what this is going to do is it will, at the end of each of these blocks, it will stick this value A under slopes, stick this value B under intercepts, stick this value R squared under our value or at the end of this list, okay? And, you know, take your creative freedoms. If you want to put all of this in a one big for loop, do what you want. Just, there are many iterations to this logic. Just feel free to do what you want as long as it works. It works. You can troubleshoot it. Go for it. And I'm going to copy these 3 lines at the end of every block. So I did it for this figure here. I'm doing it for the middle figure. Then I'm doing it for the last figure. Right? So I did this for the 3 figures. And now if I run this, I should have 3 lists. First one called slopes, and I'm calling it here. So now I'm in the shell in the bottom right. I need to figure out a way to make this bigger, but let's, you know, maybe zoom in on the video or something. So I'm going to have slopes. If I call the slopes list, I should get a list of 3 values, which are the slopes of these three lines. First value is the slope of this line. Second value is the slope of this line. Third value is the slope of this line. Intercepts, if I call intercepts, I'll get the 3 intercepts. So, you know, this value here, this value here, and this value here, right? The 3 intercepts. Maybe not here, it's the intercept at 0, right? Starting at 800. And if I call R values, gotta get the 3 R squared values. First one, 0.91 is the R squared value for this line. It's a pretty good fit. I just have one outlier here, which is really messing it up. That's how it is sometimes with experimental data. You might want to double check this point to remove it if you're running an experiment. Anyways, second one, 0.99, which is this one. You can see it's very high because the line represents the data very well, you know. It really fits it nicely. And the last one is 0.89. Again, it's a reasonable fit. However, I have a bunch of outliers in my experimental measurement due to experimental error. So maybe I want to double check this point before finalizing the fit for this line, etc. Okay, so I have 3 lists: slopes, intercepts, or values. Right, so now let's put them in a table. And the syntax to draw a table is, first of all, you need to create a list of headings, right? So what do you want to have the headings at the top of this table be? Okay, and this is very, very important. So I'm gonna have the list of headings be refractive index. Second will be frequency in gigahertz. And the third heading will be velocity in meter per second. And the reason I want these headings to be this way, it's because I want to list the slopes at the bottom, right? Or list these 3 values at the bottom, okay? And now I'm gonna import some data. So data, I'm gonna create a big list here. First thing, I'll call it metric. And this will be names. So this will be, I'll have my first row at the top having these 3 values. Second one, it will be slopes. And this will be, be careful where you put this, slopes. Third one is intercepts, right? And here I'll have my intercepts list. Fourth one is R values. And here I'll have R values, right? So I created, basically, I arranged my lists. So I'll have my first line at the top containing this heading, refractive index, frequency, velocity. My second line will have my slopes. My third line will have my intercepts, and my fourth line will have the R values, right? So now if I So once I have these, I need to arrange them in a data frame. And the way to do it, you can call this anything you want. I'm using df as, again, df is a name. It's not a function. You can change it. You can call it what you want. PD, I'm calling the pandas library now, dot data frame. And this function will create a data frame. And you give it the data, which is the name of this combination of lists which we created. And then you need to print it so that it shows print df. Let's print it and have a look what we're going to get. And as you can see, we're getting a table here at the bottom. You can see refractive in metric, refractive index, frequency, velocity, and the slope for each one of them, the intercept for each one of them, the R values for each one of them. Okay, and this is really a nice table which you can use to present your data, right? And because we're using Spider, there are of course different styling methods. You know, if you look online, find a lot of different functions to style this data frame. Maybe you want to add some lines between them, etc. But really, when dealing with data frames to present data, Spider might not be the best tool. Jupyter is the better tool. However, we haven't dealt with Jupyter yet. Hopefully we'll get to it before the end of the semester. And with Jupyter, you can really create an Excel type looking table. You can highlight them, you can highlight the maximum value, you can change the colors, you can do many types of things, change the font, etc. So it's sort of more robust when it comes to styling. However, Spider is will give you the data frame in a very sort of bare bones type of way. Okay. So this is the table we created, and this is the end of this lab. So we created the three figures side by side. We determined the linear fit, the R-squared value for each linear fit, and then we put all our results in a nice table here at the bottom. Okay, let me go to the lab here. So we've achieved these two. And for your homework, I want you to repeat this exercise for 139.9 and for KCL as well. So you should generate three plots, each one is 3 by 1, and 3 tables containing the slopes, the intercepts, and the refractive index for these 3 experimental data sets. Okay. If you want to put all of the tables at one, you want to create a, I don't know, 3 by 3 figure, again, take your creative freedom. Just make sure you're able to troubleshoot the code, make sure your code is robust. Please send me your Python scripts as a Word document with your results or send me your results in a Word document, clearly presented, and stick the Python script at the end of the Word document. Put some effort in presenting your work in a clear and organized manner. Don't forget your name at the top, etc. And if you have any questions, you're having any hard time, please come to office hours every day from 5 to 7. You can always schedule office hours by appointment. We can always talk if you want during the weekend, or reach out to me by email. Just feel free to reach out anytime, and make sure you're on track. Okay, so this is the end of this week. Thank you all very much, and I'll talk to you next week. Take care.